Hello all. We are going to be studying heating curves today, which is it's basically just a kind of graph, but on that graph there is a lot of detailed information about the way substances change as they move from the solid phase to the liquid phase to the gas phase. It's going to involve a lot of discussion of energy and particle arrangements. So let's get started. We do have a homework associated with this lesson, but I don't think that we'll be ready to do it the next time I see you. But still, write it down on a separate piece of paper, which you'll label classwork, and we will do it on the second day of this lesson. So the aim today is water heating curves. Please copy that down just under the homework assignment on your separate page for classwork. And these particular do now questions, I also want you to copy down, and we'll be able to complete those in class tomorrow. This slide's about energy and phase changes, and this extremely bold passage right here, which is the definition for temperature, is absolutely required in your Cornell notes. So it says that temperature is defined as a measure of the average kinetic energy of a substance. There's a lot of things that this does not mean. This does not say that temperature is a form of energy. It doesn't say that. Heat is a form of energy. Temperature is just a way that we can measure the average kinetic energy of a substance. So its unit is something like Celsius or Fahrenheit, whereas units for energy are always going to be in a particular unit called joules. And many of you have probably never heard of that before. It's symbolized with a capital J. So any form of energy receives this unit. And since temperature has a unit in Celsius or Fahrenheit or even Kelvin, which some of you may have heard of, that's evidence right off the bat that temperature is not a form of energy. So to get us started, I want you to consider that oxygen is a gas at room temperature, but water is a liquid at room temperature, and iron is a solid at room temperature. How could we get away with saying that solids have less energy than liquids and liquids have less energy than gases? The answer to this question is not going to be about kinetic energy, which is the energy of motion. And I can say that for sure because we are saying that they're all at equal temperatures. And therefore, if they're all at equal temperatures, then they must have the same average kinetic energy. So I'll write that first. It's not about kinetic energy. But there is another kind of energy, and it's called potential energy. And potential energy is stored energy, and some think of it as the energy of position. One way to visualize this is to think about a rock in two scenarios. One rock at the top of a hill, and one rock at the bottom of a hill. Although at this moment neither one of the rocks is moving, you can easily assess which one has the potential to move. And what you're really doing is you're making sense of the potential energy that's stored in the distance between the rock at the top of the hill and the ground. So similarly, two molecules that are very far apart from one another, such as in gases, the distance between the particles actually stores some energy. So the farther apart particles are, the more potential energy they have. And that's why we can get away with saying that gases have more energy than liquids or solids. And so I just added more separation, more potential energy. So the difference between kinetic and potential energy is pretty simple. Kinetic energy is the energy of motion, and potential energy is the energy of position. So the forces that must be overcome in order to spread particles out from one another, or in other words, to increase their potential energy, are intermolecular forces. And since you must spend energy in order to separate particles that are attracted to each other, then the process is considered endothermic. So the question here is, where does all that energy go? How is the energy that is absorbed, or I would say given to the substance, used? It's used by storing it in the distance between the particles, so it's used to increase potential energy. So here are some terms that you're going to need to understand phase changes. First of all, the difference between freezing and melting is basically nothing except for the direction that you're going. You can see that here. If I'm going from liquid, which is this section, down to solids, I have to pass through freezing to get there. And if I want to go from solids up to liquids, I have to pass through melting to get there. But there really is no difference between freezing and melting. They actually are the same thing, they're just two different directions. Additionally, the difference between condensing and boiling is really not much of a difference. It's just a directionality issue. So the heat of fusion, this is a very important term, and it has nothing to do with the fusion that you already know, which is when two nuclei come together. Instead, this kind of fusion is relating to the process of freezing and melting, and it's the amount of heat required to melt or freeze 1 gram of water at standard pressure. So I just wrote this definition down, but one thing I did add was that heat is measured in joules. Oh, I forgot the word heat. There we go. The amount of heat in joules, which is the unit to measure heat, to freeze or melt a gram of water at standard pressure. I want you to copy down this diagram in your notes. It's a lot more detailed than the ones you'll see on the Regents. The ones you'll see on the Regents are mostly just the line only. But I think that getting a sense of these particles is really important, because one of the things that you will need to do on the Regents is be able to draw something called a particle diagram in certain short answer questions. And particle diagrams are literally this, that, and this. And almost every Regents will ask you to draw a particle diagram, so I think it's great to associate it with the heating curve now. So, in this particular slide, we're going to take a look at a more Regents style heating curve, but we're going to talk about potential and kinetic energy changes. So the graph shows what happens to temperature of a substance as it's heated constantly over time, so the amount of heat that it's absorbing is very constant. The line segments on the graph that indicate increases in kinetic energy are this one, and this one. And the way that you can tell that is because the y-axis is temperature. So if you see a line which is increasing on the y-axis, then it's increasing in temperature, and temperature is defined as average kinetic energy, the measure of average kinetic energy. Therefore, if temperature is increasing, so is average kinetic energy. The line segments on the graph that indicate changes in potential energy would be BC and DE. Now this one's a little bit trickier. The reason I know that is because the substance is being heated constantly over time, so the substance is absorbing heat at all moments. During sections A, B, C, D, and E, F, it's obvious the way that it's absorbing heat. It's using the heat to increase kinetic energy. But even in section BC and section DE, the substance is still absorbing heat. But you can tell by the line being flat that it is not absorbing kinetic energy, because the temperature is remaining constant in those sections. So if it's not absorbing heat for increasing kinetic energy, then the heat must be being used to increase potential energy. One thing I like to think about when we talk about this is that if potential energy is increasing, that means that the particles are spreading out. And I am saying that because the potential energy is the energy of position. It's the more distance between two things, the more potential energy they have. So down here we have solids, and here we have solids that are spacing out and turning into liquids. So here we have liquids, but up here we have liquids that are spacing out and turning into gases. and then finally we have gases up here. Heating curves are always endothermic because at all points during this process, heat is being absorbed. All right, we also need to discuss what are the actual phases of matter in these particular phase change diagrams. The line segment that represents solids only is line segment AB. I can say that for sure because it has the lowest kinetic energy of anything on this graph. And I know that as a substance is heated, it changes from solid to liquid to gas. So I know section AB is the solids. Similarly, the line segment that represents liquids only would be line segment CD. And it's similar to the solids line, just in a different position. And lastly, the line segment that represents gases only is this line segment, EF. And it has the most energy of all of the phases present on the graph, and that's how I know that it must be gas. But the line segment that would represent melting, which is also called fusion in the Regents, is going to be line segment BC. The way that I know that is because it's the transition space between solids and liquids. So that process, as solids change into liquids, would be called melting or fusion. And so for my reason why, I just said it's showing that solids are transitioning to liquids, so that's the fusion point. And similarly, the line segment that would represent vaporization would be this line segment, because it is the space that separates liquids from gases. So, the heating curve summary is going to serve as our pair-up for today. Just copy down this sort of bare bones slide right here that just says A, B, B, C, C, D, D, E, and E, F. And you will also need to have the diagram from the previous slide copied, otherwise you won't be able to do this activity. So copy down the diagram from the previous slide as well as this slide, and it'll serve as our pair-up. And this is our summary. Please copy down everything you see on this page and have it ready on that separate piece of classwork paper for tomorrow. Thank you for watching.